All right, part 2, equilibrium, which is how far a chemical reaction is going to occur. We're going to describe why a chemical reaction eventually reaches equilibrium and then relate K and Q data to each other given data. So if you look at this picture of our ants working hard here, we have one ant taking from the reactants and going to the products, and we have one ant going from the products to the reactants. If they keep doing this at an equal rate, they would be at equilibrium. So chemical equilibrium or dynamic equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction in a chemical reaction, meaning we have reactants going back and forth at an equal rate, meaning the concentrations of the reactants and products are going to be consistent. Now, chemical equilibrium is determined and set at specific temperatures, meaning that if I change the temperature or if the reaction was happening at a different temperature, the chemical equilibrium would be different for that reaction. So when we look at chemical reactions here, let's look at this example. We're adding A and B together. At the beginning of the reaction, no products have formed yet, and there's going to be a high rate of collisions between those A and B molecules, resulting in a high forward trend in this reaction, meaning all of the reactants, not all, the reactants are all colliding with each other to form products. In the middle of our chemical reaction, we get to this kind of messy point where we still have our reactants colliding with each other, but at a lower rate because there's a lower concentration of them. So we have less reactants forming products, and now we have some products reacting with each other to form and go backwards into reactants. So in this case, we have a little bit of forward and reverse, and once we reach that dynamic equilibrium, it's when we have equal amounts of reverse and forward reactions, and that is when our concentrations are going to be consistent. So there's this thing and this idea of equilibrium position where I say equilibrium and we think of equal, but sometimes that isn't always 50-50. It doesn't mean that I have equal amounts of reactant and product for this chemical reaction. It just means at that equilibrium, it might favor or prefer one or the other. So if we think about the acids and bases we talked about in our last learning target, if we look at this top one here, this 80% means that the products are favored to the reactants. This would be a strong, weak acid, meaning not a strong acid. It's still considered weak because it's not 100% ionizing. About 80% of it, in this case, would be forming products, and 20% would stay as reactant. The opposite can also be true, where a reactant is favored over a product, like in the second example here. This would be a very weak acid, where only some of that acid is ionizing and becoming hydronium in solution. This would have a much closer pH to 7, where this one here would have a pH closer to that 3 to 4 range. And so it's the point in the chemical reaction where the reactants and products are no longer changing. That is that equilibrium position. So how can we represent and show this K or equilibrium value? We use K, or big capital K, to represent this equilibrium constant, and it's the ratio of the concentration of the products over the reactants at equilibrium. Again, it needs to be constant, or it is constant until the conditions such as temperature are changed. So if you change the temperature, your equilibrium constant will change. So you always need to make sure that you are at a set temperature. When writing your equilibrium expression, you exclude solids and liquid water. For you guys, I'm only going to give you ones that are gases so that you don't have to worry about this. So this is an example of how to set up your equilibrium expression here. We have a very basic chemical reaction where we have A plus B producing C plus D. The lowercase letters in front of our reactants and products are the coefficients that would be used to balance the chemical reaction. So when we write our equilibrium expression, we set K equal to the concentration of those products over the reactants. So in this case, our products are C and D, and our reactants are A and B. Again, remember we are raising those to the power of that coefficient. So C is raised to the power or the coefficient of C, D is raised to the coefficient of D. And we'll practice doing this on the next slide. When we calculate our K values, or when K values are given to you, if K is greater than 1, that means that our products are higher. Our numerator is big and our denominator is small. That's going to make K larger than 1, meaning that our products are favored. We're going to have a higher concentration of products at equilibrium. If my K value is less than 1, that means that my denominator or my reactants are in higher concentration than my products, the numerator. That is going to lead to a higher concentration of reactants at equilibrium. If my KEQ value is 1, that means that at equilibrium I'm going to have equal concentrations of both reactants and products. So let's take a look at calculating one of these. I included the little guide here up in the corner so it can help us out. So we're writing the equilibrium expression to calculate KEQ if there are 0.01 moles of N2O4 and 0.24 moles of NO2 in a container. So we have our reactants and our products. In this case, we just have one reactant, one product. This is a weird decomposition reaction that can occur. So we need to set up our rate expression to start. So we need to put our products over our reactants. And so we have our NO2, which is a product, raised to the second power because of its coefficient, over my reactants, not raised to any power because there is no coefficient. I'm then going to plug in the values for my molarity. Now notice that I didn't give you molarity, I gave you moles. However, molarity is moles over liters. So if I take this value of moles and divide it by 1, I get the same value. So again, just make sure that you're using molarity inside your brackets when calculating these values. So you plug in the values. I had 0.2 moles of my NO2 raised to the second power. Don't forget to include the second power. And then I'm dividing that by 0.01 moles of my N2O4. Simple math, guys. Just type it in your calculator. Make sure you use parentheses. And you should get a K value of 4. This means that my K value is greater than 1, so are my reactants or my products favored in this type of reaction? Products. Products would be favored in this type of reaction because my numerator, in this case, is larger, meaning my products are being produced at a higher rate, so I'm shifting towards that product side on this type of, in this example, reaction. There's another value we can calculate and use to kind of see where we are in a chemical equation, and that is the reaction quotient. It is the ratio of products to reactants at any given time during a chemical reaction. So the difference between the quotient and the constant is that the constant value, the K, is at equilibrium. The reaction quotient is what we calculate if we don't know if we're at equilibrium. Sometimes in the middle of a chemical equation, we don't know where we are, and so we need to calculate to see if we are kind of right at equilibrium or if we're going to shift towards reactants or products. And so it's evaluated to see which direction the reaction is going to go, and the value changes as the reaction proceeds. At the beginning of the reaction, your Q value is going to be less than K because you're going to have more reactants than you have product. When the reaction is complete or is like past complete because of standard conditions, you're going to have more products than reactants, and then your Q would be bigger than your K. So I like to look at this first example up here where you look at this little alligator. So if your Q value is greater than K, you are going to proceed to the left, meaning that products are favored, so the reaction is going to go towards reactants to try to balance the reaction out. If your Q value is less than your K value, that means that your reaction is going to proceed to the right towards product because reactants are favored. And so it's like the opposite, right? And so being able to say what those things are is helpful, and being able to identify which direction you're going based on your Q value. So let's look at an example here. We are, if we measured 2 molar N2, 0.002 molar H2, and 0.052 molar NH3, which direction will equilibrium shift? So we have a balanced chemical reaction here, and we're given our equilibrium value. So what we're trying to figure out is, are we at equilibrium, or is our reaction going to shift towards products or reactants based on our given measurements at that moment? So always setting up, your first thing is writing your equilibrium expression. This one's a little bit more complex than the prior one. We have our product, we have just one product, our NH3 to the second power, and then we have 2 reactants. We have N2 and H2 is raised to the third power. I wanted to add this little multiplication sign here just so that you knew that when we put things right next to each other in science, we don't always add a multiplication symbol, but it is implied. So let's plug in the information we know. We have a 0.05 molarity NH3, 2 molar N2, and then our 0.002 molar H3. Don't forget your coefficients here. Do the math, and you should get 6.76 for your Q value. So our Q value is greater than our K value in this case. Our Q is 6.6, our equilibrium value is 0.064, so it's quite a bit larger. Meaning that, which one is favored currently? If my Q value is greater than my K value, that means that products are favored and that the reaction is going to shift towards the left to the reactants. So if products are currently favored, my reaction is going to shift to reactants before it reaches equilibrium. All right, so this last piece we looked at a little bit in our virtual lab, and it is, how can I modify a reaction to make more product or less reactant? And this is really what scientists use this idea of equilibrium for. If you're working in industry and you're trying to make products and you want to make sure you're making more products than your reactants, what can you do to that chemical equation to shift the reaction so that it produces more reactants, more products, whatever you're looking for? And so there are a couple things that we can change in a chemical equation to increase the amounts of products at equilibrium. And so we're going to look at this little image here. And I really like this little image because it kind of talks about what this principle is. So Le Chatelier's principle is when a system is stressed, meaning something is happening to your equilibrium system, the reaction is going to respond, just like we do. So if we have a happy system at equilibrium, and then a stress comes along and is like, oh no, what's happening? We're being stressed. What's going on? Changes in concentration, pressure, and temperature can cause a stress to a chemical reaction, which is then going to create the reaction not being at equilibrium anymore. So if a reaction becomes stressed, what's going to happen is that your K value is going to change. So if concentration and pressure changes, your Q changes. If temperature changes, your K is going to change as well. So what happens in that chemical reaction? A response. So if your Q value is less than K, the reaction is going to go in that forward direction. And if your Q is greater than K, then your reaction is going to go in the forward or reverse direction. So again, that Q versus K relationship is still present. So if I increase temperature, if I change concentration, and if I change pressure, my reaction is going to respond accordingly. Eventually, the system will then figure itself back out where Q and K are getting closer and closer, and then eventually you'll get back to equilibrium where your Q is equal to your K value. So this is known again as Le Chatelier's principle, a French term for those of you that are French speakers. And these are the different stressors and then what is happening and why they happen. So take a second to check these out. Sorry, I'll keep moving myself so that you can pause it. There we go. Now I'm not in the way. So these are all the different things: concentration, pressure, temperature, and actually a catalyst does not change the forward and reverse rates. So I wanted to include that one on here. So pause the video, check these out. The last thing I want to show is this little infographic. And I included the link to this infographic in the notes guide so that you can zoom in and read all of these things. So it talks a little bit more about equilibrium, Le Chatelier's principle, then it talks about the concentration, temperature, and pressure and how they can affect a chemical reaction. I'm not going to ask you specifics about each of these. I'm going to ask you kind of what they are and to give me a brief overview of what happens, but this gives you a lot more information on what is happening if you shift and change those chemical reactions.